But what about the symmetric stretch? Does it change the dipole moment? No. So the symmetric stretch will not be IR active. So the only way it can be IR active is to think of a vibration that is going to lend a dipole moment to this molecule, and that would be. And I've always told you, don't just write this and leave it there. So this actually means the molecule is moving in this direction. So you must say a little thing out here. Essentially meaning that this bond is extending, but this bond is contracting. So if you don't put these two arrows, it essentially means the molecule is transferring along one of the axis. And that's not what I asked you. I asked you for a vibrational mode. And therefore, if you don't put this, it's a big zero, because it's not a vibrational mode. So be very careful in the way you depict the vibrational mode. You've got to be careful the way you say things, and that's very, very important. At the end of the day, the precision in what you're saying is very important. So this is an anti-symmetric stretch where one bond shortens and the other bond lengthens at the same time, and therefore the molecule does have a dipole moment. Because of that, this is IR active. But the same bond, the same vibration will not be Raman active, because it's already IR active. I know that. And if it is IR active, the principle of mutual exclusion will immediately tell me that such a molecule, such a vibration mode in this molecule at the center of symmetry would not be Raman active. So these are things you can expect to see. I can give you a molecule, I could show some vibrations for which it's very easy to figure out whether the dipole moment will change or not. I'm not going to give you a very complex cholesterol or protein molecule and a very weird vibration mode and ask you will this vibration be active or not. I'll give you a simple molecule. Just by looking at it, you must be in a position to say whether this molecule will change its dipole moment or not. And that is something you will be called upon to make a guess. Nobody is going to ask you about intensities. All you have to say is whether this will be seen or this is likely to be seen in the infrared spectrum or Raman spectrum. Then of course the carbon stretch, which I'm sure you already have seen in the lab already, in many of the compounds that you might have been looking at. I don't know what compound you looked at an ester or a ketone, so on, and you see the carbon stretch coming roughly around 1700 wave numbers, give or take a few 10 or 50 wave numbers, depending on to what it is conjugated to. If it is conjugated to an NH, to an amide carbonyl, then you know it sort of moves lower because of the fact it will have a resonance. But at the end of the day, the carbonyl frequencies are generally around 1700 wave numbers. And anything which you see is very strong at 1700, you know you are looking at a molecule with a carbonyl group. And it is strongly IR active for the simple reason that the carbonyl group does change its dipole moment when the molecule vibrates along the CO coordinate. It's a very strong change in the dipole moment. It's a very strong vibration, and it's almost a telltale vibration in the vibrational spectra that you can see this carbonyl quite easily. And the last one I think is the rhenium stretch of the inorganic cluster. Rhenium stretch again, he says, neglect everything else, this is what he should be saying. And you're just looking at the rhenium bond, but again the rhenium bond would not change any dipole moment for you, and therefore one does not expect to see that in infrared spectra. Of course, the rhenium bond, mind you, even if you could see it somehow, not in the machine that you are looking at, the machine that you are using in the lab, what's the frequency or what's the wave number range of the machine? 4000 on one end and 400 on the other end. It could of course go to 7000 or 8000, but if we just plot 4000 to 400, the machine can actually give you about 7000 or 8000 on one end. We don't plot it because we don't expect to see any vibration in that region. And on the downside, you see above 400, maybe 350, that's where we cut off. But a rhenium bond, if you did have a vibration that you could observe, it's not going to be this region. It will probably be less than 300-400 wave numbers. It will show up in the far infrared region. And that's very typical of most inorganic compounds, but you will see them in the far IR or the far infrared region. Simply the heavier mass takes these frequencies to much lower wave numbers than what you would expect to see for an organic compound. So the rhenium, even if you could see it, this machine that you're using will not let you see it because it's not even looking in that window in which the rhenium bond has to absorb the infrared radiation. It's going to be in the far infrared, and the far infrared is somewhere from 50 to about 600 wave numbers. So 50 to 600 is far IR, 400 to about 7000 is mid IR, and about 6000 to about 15,000 That's the near IR. The near, mid, and far all have to do with the UV visible range. The 15,000 wavelengths is close to the UV visible range, therefore it's called near IR. So all these nomenclatures that you have, they are all based on where this electromagnetic spectrum is relative to what you can see. It's all relative to the UV visible region. The same way if you go to the vacuum to the other side, you'll have near UV, far UV. The far UV is the one that's furthest away from the UV again, and it's something like 200 nanometers away. So don't remember numbers, but just have this thing that if you have a visible region out here, the one that is closest to the visible on the low frequency side is going to be the near IR, and on the very far side is the far. And inorganic compounds generally will show you the far IR region. And what's the big difference in the machine that you're using between what you have now that you're using and the one that you use there? The optics has to be different. Because the present optics, why are you stopping at 400? Who's stopping you at 400? The optics is stopping you because the optics is absorbing everything beyond 400, and therefore you can't get that light to go through. So you've got to change the optics, you've got to change the beam splitter, you've got to change everything else on the way so that they don't absorb. What you have now is a KBR window inside. You have a KBR beam splitter, you have everything made of KBR, potassium bromide, which is also the thing that you're using for making pellets, which is also the thing that you have for your windows, for the liquid cells, and so on. So if you're going to use far IR, it can't be KBR, it has to be something else. And it turns out that if you use polythene, that's the best optics. So that's as far as the instrumentation. So the next one is an A2B2 molecule, something I've already drawn up. And what he has said, don't worry about this PR contour and the PQR contour, because that again has to do with something that you have to learn in greater detail. But even without that, you'll be able to figure out what this molecule is. First, it's an A2B2 system. And what do you see from the pattern given to you? Any feature that is strong in Raman doesn't seem to be there in IR. And any feature that is marked as very strong in the infrared region, it's not there in Raman. So immediately what does this tell you? That this molecule must have a center of symmetry. And of course I told you it's A2B2, so it's something like C2H2, and this must be the structure of the molecule because it must have a center of symmetry. I can't twist this molecule in any other way and get a center of symmetry. So straight away I know that this molecule must have a center of symmetry. So the very fact that it is A2B2 and it has how many vibrations? It's 5 vibrations, and it clearly tells me that one is missing, the other one is there, and vice versa. Tells me the molecule must have center of symmetry. Take 4.7, which is again an AB2 molecule. And clearly in this case you see that infrared, all the features are seen. Whereas in Raman, you see one that is strongly polarized, whereas two others you don't see them. Now it doesn't matter why you don't see them. The reason as to why you are not seeing them in Raman is not the issue. The issue here is that there are features that are common to both IR and Raman. If they are both common to IR and Raman, then clearly this molecule just cannot have a center of symmetry. Because if it had a center of symmetry, then there must be some missing lines in one which you see in the other, and vice versa. Surely the feature at 3652 is seen in both, and that rules out the possibility that this molecule will have a center of symmetry. So if it does not have a center of symmetry, there are only two possibilities you can think of for an AB2 molecule. Either it is bent or it is linear. If it is linear, you are in trouble because then it has a center of symmetry. Of course, you can always ask me, what about a molecule such as this? That doesn't have a center of symmetry. It can also be linear. So then, with the data that you have over there, it's not going to be so easy to figure that out. So at least the information that you're going to be able to give me with this is that I have a structure that is not going to have a center of symmetry, and one possible structure is AB2, which looks like certainly this structure will obey or will be consistent with the data I have given you. So if you give me that, it's fine. But of course, if you give me something like this, I'll still be able to, and if you, of course, you give me the argument that this molecule does not have a center of symmetry, then there is something that you can talk about. But how many vibrational modes does this molecule have? It must have, and that has 3. And if it has 4, 2 of them would be degenerate, of course. You can always argue that 2 of them are degenerate, and therefore I see only 3 and there are 3. But if I now tell you 3656 non-degenerate infrared vibration, 3652 non-degenerate, and 1595 non-degenerate, that is enough of an information to decide that it can't even be this and it has to be only this. Because if it is this, I must have 4 vibrations, either 4 separate ones or 2 of them non-degenerate and 1 of them degenerate. But if I tell you there are 3 vibrations which are non-degenerate, then it straight away tells me I only have 3 vibrational modes for this molecule, and a triatomic molecule with 3 vibrational modes straight away means that molecule cannot be linear. So if it is linear, it must have 4 vibrational modes. So that is some information I could give you, which is not given in Banwell, but I could give you that information. And with that information, if you give me ABB, you get nothing. Because with that information that I have given you, it just can't be an ABB molecule. Saying that ABB has no center of symmetry, therefore it must be consistent with what I have, will not be acceptable, because ABB must have 4 modes, but I gave only 3 modes, therefore that would be wrong. So if I give you the data that there are 3 non-degenerate modes, then straight away you have to decide between a linear and a non-linear molecule. And the only answer that in that situation is that it would have to be a non-linear. The 4.8 again has to do with some PR structures, so we will not worry about that. So the questions that I have discussed, these are the sort of arguments that I would like to put forth, depending on the sort of molecules and sort of examples that I will give you. Now I will try to factor in all these arguments in this quiz that I am going to give you on Monday. And do take it. And as I said, we will have the quiz for the first half hour, and the second half hour we will discuss the quiz. And not second half hour, maybe 20 minutes, and the last 10 minutes, as I normally like to do, I will quickly summarize what went on in the second module of this course, and then that will sort of help you to figure out how you go about preparing for this exam. It's quite hot, and therefore I am quite comfortable. Because that's the place where I come from. It's always hot and humid. That's perfectly okay with it. I remember coming on day 1 of class in 2009, I was sweating. And some of people down in the south, you always keep thinking every place up north is cool until you come here and then you find that it is not very different. It is as hot and humid. And I remember taking the class, this place wow, is very hot and humid, and therefore I am very comfortable. Okay, let's get back to electronic spectroscopy. We already did the hydrogen atom last time. And what did we do for the hydrogen atom? We said the hydrogen atom has a very interesting energy level picture. And what is that picture going to be? So 1s, 2s, and 2p, which were degenerate because it's a 1 electron system. And any 1 electron system will have a situation like this. And we also said that while in school you might have learned about these Lyman series, Barber series, where just one level goes to another level, and you look at it only in terms of n. Now you have to start looking at it in terms of n and l, even though these various levels corresponding to different L values are degenerate. 2s and 2p are degenerate. That's for the hydrogen atom. So once you get to the helium, the story begins, and then everything gets split, and then you need a Rockoff principle, and so on. And then we said there's a selection rule on these transitions, very much akin to the selection rules you have seen earlier for rotational spectroscopy, which involves angular momentum initiates. And we said that delta L must be plus minus 1. Keep this in mind because we're going to be looking at it again when we come back for poly-electronic systems, not one electron system. Delta L plus minus 1 has to be obeyed. If delta L plus minus 1 has to be obeyed, what happens to the transition? It has to be only this, it has to be this, it has to be this, and so on. This can't go to this, because if it goes to this, there is 1s to 2s, and 1s to 2s is delta L 0. Can't happen. 2p to 3s has to happen. 2p to 3d has to happen. In a way you can understand this based on the symmetry of the orbitals. S orbital? Is it symmetric or anti-symmetric? Symmetric. What is the P orbital? Plus on top, minus on top. Plus over here, minus over here. Plus up here, minus up here. Because the P becomes anti-symmetric. So if I'm really looking at a transition from one level to the other, what's the integral I must really be looking at? Something like that, and evaluate that. Again, the dipole moment operator comes in because the dipole moment operator is the one that's actually driving this whole transition. 1s is symmetric, P is anti-symmetric. And what is mu? Dipole moment operator. If I change all the coordinates, the dipole moment, which was probably pointing in one direction, I switch the coordinates, it just becomes anti-symmetric. Therefore, this is anti-symmetric too. So if I have symmetric into anti-symmetric, what happens to the whole integral? It becomes symmetric. Something like what we learned in the last symmetry course a month or so that we had. So it is symmetric into anti-symmetric is symmetric. Symmetric into symmetric is symmetric. The whole integral is symmetric. And if you go back to revisit your mathematics, you will find that if you had a symmetric integral, it doesn't necessarily have to go to 0. You have a small value, but it's not going to go to 0. But an anti-symmetric integral, something like this, which flips sign, if I integrate this, what's going to happen? This will have to go to 0. That's the reason why integral of sin x or integral of cos x over an even interval, you will see in one case it goes to 0, in another case it does not go to 0. Use those concepts. So if this is symmetric, anti-symmetric, the whole thing is symmetric, and therefore there is no reason for this guy to go to 0. However, I'm trying to make a transition from 1s to 2s. What will happen? Symmetric into symmetric is symmetric, into this is anti-symmetric, whole integral is anti-symmetric, looks like this, therefore the integral vanishes. Therefore you can simply use symmetry arguments to decide whether this integral is going to go to 0 or it doesn't necessarily have to be 0. Every time I have a delta L plus minus 1 selection rule, you will find the integral need not necessarily go to 0. I'm using that word need not go to 0 because it might have a very small value such that you can't even see it in the next parameter. But the evaluation of the integral does not tell me a priori that this integral has to be 0. But if it is anti-symmetric integral, then don't even bother about looking at it. It's going to go to 0. Throw it away and go on with your other jobs to do. It doesn't work. That's the reason why 1s goes to 2p, 2p goes to 3s, 2p can go to 3b, and so on. You don't have a situation in which 1s goes to 2s, or 2p going to 3p, and so on. You must have a delta L plus minus 1 variation to be able to see the transitions in this sort of a system. But then we also said, no, look, this is too naive. This is not the way we should be looking at it, because by now we know how to handle term symbols. And we said, don't keep on saying 1s, 2s, 2p, 3s, and so on. If I have one electron sitting in a 1s orbital and that's it, what is the state of the system going to be? A doublet S, 1/2 state. So if I have one electron sitting here, it's also going to be a doublet as 1/2 state, excepting the electron is in n equals 2. Put it up here. It is still doublet as 1/2 state, excepting that the electron is in n equals 3. So all these states, whether the electron is here or here or here, it's all going to be doublet as 1/2. Where the 2 on top represents a 2s plus 1 value. The s tells me that the orbital angular momentum is 0. And the half actually tells me the total angular momentum. What happens if I have an electron here, one electron here? That will be a doublet P. How many possibilities? Right? Now which of them is going to be the lower energy state? 1/2, because it's a P1 system, it is less than half full, therefore it must be a doublet P 1/2 ground state, and a doublet P 3/2 is going to be the excited state. If I had a P5 system, like what we have in the case of the halogens, then it's going to be again a doublet P, because the whole formalism is there. P5 behaves just like P1, and therefore if P1 is going to give me doublet P 1/2 and doublet P 3/2, then P5 must also give me doublet P 1/2 and doublet P 3/2, and the only difference between these two systems is going to be that WP3½ will be the ground state, the lower energy state for systems that are more than half. We have seen all that. I'm just trying to recall whatever we did the last time around. And this is what is going to happen. So now when I ask you, what is this transition? I don't want you telling me it's a 1s to a 2p transition. I want you telling me it's a doublet S to doublet P transition. And what is more, since this is not one level really, there's actually two levels. Because it's doublet P 1/2 and doublet P 3/2. So you will have two levels out here. So if you look at the 1s to 2p transition, which is actually a doublet S to doublet P transition, and if you look at it in very high resolution, you will actually see two lines in there. And those two lines are basically transitions that are from doublet S 1/2 to doublet P 1/2 and doublet S 1/2 to doublet P 3/2. Two lines. And you will see that. I did mention to you earlier on, if you look at sodium for example, what's the electronic configuration for sodium? It's an S1 configuration. You don't have to worry about 1s2, 2s2, 2p6 and all that. It's got an S1 configuration. And if it's an S1 configuration, a 3s1 configuration, and I kick the electron out of that orbital, where does the electron go? Let's say it goes to the 3p. So what am I really doing? I'm doing a doublet S to a doublet P transition. But doublet P is again a doublet P 1/2 and doublet P 3/2. So if you take a sodium emission and look at it in high resolution in a spectrometer, you will actually see two lines, one of which corresponds to a doublet P 1/2 to doublet S 1/2 transition, and the other one will correspond to a doublet P this way. This is the P1 configuration, this is an S1 configuration. So you will see those two lines, and it is the splitting of that line into a doublet that actually tells you that I'm actually looking at sort of a doublet configuration for this particular transition. And you will actually see two, I think it's like 589 point something and 590. Very, very small split, but large enough to be clearly resolved in most medium resolution spectrometers. You will be able to see that. What do we expect to see in potassium spectra? Same thing. This is again a doublet S to a doublet P transition. You will again see a doublet, you will see two lines, but the two lines will be at in a different region of the spectrum. And the splitting between the two lines will also be different because it's a different element with a different nuclear charge and therefore a different set of energy levels. What's the color of sodium? Not sodium emission. Don't be sodium is silver.